So hello everyone, and thanks for joining. My name is Javier Nistal. I'm an associate researcher at Sony Computer Science Laboratories, and today I will be introducing to you the Diffusion project, which is what I've been working for the last 2 years, and it is our context-aware music STEM generator. But before, let me give you a bit of context about our lab and the music team, which is the team to which I belong to. So Sony CSL is a fundamental research lab working across a variety of topics, including many, but among them sustainability, creativity, language, music, and culture, and many others like biological automata, to name another. And this lab is under the direction of Dr. Hiroki Kitano, who is also the president of Sony AI, the director of Sony AI. And it operates in Tokyo, which is its oldest office, almost 40 years, 1989. Then Paris was the next one, Kyoto, and very recently an office in Rome. So such mix of disciplines at the lab and the particular ethos of the CSL lab allows us, the music team, to approach music technology research in a very unconventional way that may look more like a craft rather than actual only science. Of course, we stick to scientific methods, but it's more like a crafting technology lab. So the music team combines a wide variety of disciplines and expertises, and combines researchers, engineers, musicologists, producers, and many masters and PhD students. We also have a strong partnership with other divisions within Sony, as well as other companies, like, for instance, Steinberg, with which we released a couple of years ago a plugin with them, Drumgun. We, as the music team, build creative tools for music production, generally involving AI, but not only, and that include music companions, synths and samplers, signal processing tools, lyric writing tools, and music analysis. Diffusion, the project I'm about to present today, sits with the creation tools like drumnet and bassnet, but it targets multi-instrument accompaniment generation with fine-grained control. So, by the way, we are currently looking for interns for next spring, so if these topics resonate with you and want to follow a career in this path, don't hesitate to send us a note to the CSL music team address written there. So our mission in the music team is to explore creative and innovative ways of applying AI to music production, and it goes without saying that this is with controllability and the artist's musical context at the center of this. So in this regard, one of our flagship projects is, at this moment, is the Diffusion project, which is a context-aware music STEM generation system. And the central question in this work is whether can a generative model listen to an existing piece of music, understand the musical situation, and generate novel instrumental material that adheres to such context in a controllable and useful way for the artist. So this is a very common task in music production. For instance, imagine we already have some existing recording, like the following. And let's say that we want to create some drums to play along. Perhaps we have some existing sample that we have drawn inspiration from, or that we use, or that we explicitly use as a reference, like the following. So the imagined result could look something like this. In fact, this was actually produced by the model. So traditionally, to produce such a drum loop, we would need to be either a professional drummer, or we could take our chances by searching through extensive libraries, looking for the right sample, doing time stretching and adapting it to the tempo and and style of the original recording, or fiddling with complex controls in a synthesizer, all of which is extremely time-consuming, may require a lot of technical expertise, and won't necessarily yield the result we envisioned, right? So there exists quite a number of early works that have attempted to tackle these tasks with generative modeling. One of them is DrumNet by my colleague Stefan Lattner. This is a work from 2019, and it's a gated autoencoder that learns rhythmic interactions between some context input and some target drum patterns. So between a musical context and the different percussive elements. So we can see this video of the prototype we implemented. So as you can see, you have a latent space, which is the gated autoencoder's variational latent space. And basically you just give it a sound. So you have like a model per instrument. So you have kicks, snares, cymbals. This model receives the instrument you want to generate. So one shot together with the onset activation function of your context. And based on these two elements, it can basically generate plausible additional onset activations for your one shot.
Just a quick question here, like the latent space, you have like some semantic representation here, or you just...
It's just a 2D dimensional latent space, and we just plot the density under the data. So you have this topological representation. There is no dimensionality reduction. It's just a super simple 2D latent space, so you can plot it. So the same principle was subsequently applied for BaseNet. So the same principle, gated autoencoder, learning relationships between onset activations, just that in this case for baselines. So yeah, the magical thing of this model is that even if you just give it a percussive input where there is no harmonic prior content for the model to choose the specific melodies, still it keeps coherent over time, and yeah, pretty cool. This is already 2020, right? It's pretty old. So yeah, more recently, BaseNet 2 shifted to a more sophisticated latent diffusion model for better fidelity and control. Key ideas that we borrowed from this work for Diffusion, and this was also done by our lab, 2024, by Marco Passini. We can listen to a... Voila. So other works that are listening to a context to generate time-aligned content are StemGen and SingSong, are recent examples from outside our lab that also emphasize this principle of listening to a context. StemGen closely follows the discrete tokenization paradigm of music gen to autoregressively generate MIDI-sonified data. And SingSong is not really a stem generator, but rather an instrumental generator informed by singing voice recording. So, for example of StemGen. Voila. And yeah. So So as I stated at the beginning, the music team's mission at CSL is to craft AI tools for music production. And from this perspective, existing works on generative modeling exhibit important limitations that impede their deployment in professional environments. From things as obvious like insufficient sample rate, with a lot of works being below 44.1 kilohertz, or lack of stereo support, to excessively large models that incur in very large inference times, which are obviously a nightmare to use for music making, right? But also controllability issues, with text being the primary mean for interaction nowadays, which is fully automatic, and also, models that generate complete music pieces as opposed to individual strands, which are not very modular to make music with. So our work with Diffusion has addressed some of these gaps. So Diffusion generates stems conditioned on some user-provided musical audio context and some audio serving as reference of what we want the model to produce as the output, and or text description. So we can either use the text descriptions or not, and we can also do interpolations, as we will see later on, by using CLAP, that I guess most of you are familiar with. But yeah, we can do text interpolations in the latent space of this CLAP model and do a bit of a Frankenstein between an audio reference and a text description. So for instance, in this case, we could give an audio example of a classical piano, but then in the text prompt do a rock piano, and then we would get some sort of rock piano at the output with the style of the classical one, but and adapted to whatever given context. So concretely, Diffusion is implemented as a latent generative system that comprises 4 main blocks. Here, the blue color indicates non-trainable blocks, so they are frozen. So we actually only train the orange one. And as for these 4 blocks, of course, we have some training data that contains 1 million training audio pairs, subsampled from real multi-track recordings. And from these audio pairs, first are compressed into a latent representation using music to latent, a consistency autoencoder, capable of reducing the frame rate of the audio information from 48 kilohertz to by 64, so whatever that is. Which effectively simplifies the task for the latent generative model. Next, we have a CLAP, which we haven't trained. It's a pre-trained model, which embeds the audio reference into a joint text-to-audio representation space, equipping the model with natural language understanding without actually requiring per text input pairs on our training data, which we don't have. And finally, in orange, the latent diffusion model, which is implemented as a standard convolutional unit and uses elucidated diffusion models that I've seen before that you guys, some of you have been using, and predicts the latence of the target, given the compressed context and the CLAP embeddings of the target itself. So let's look at each of these blocks a bit closer. So as for the data set, we employ 22,000 multi-track recordings with a sample rate of 48 kilohertz, primarily from pop and rock genres. To create the target accompaniments and music context pairs, we subsample random sets of tracks from each multi-track using a 10-second window with a 3-second hop size. And by doing this sampling, we end up with 1 million pairs of 10-second fragments. And we normalize all segments to a loudness level of minus 20 dBs to ensure loudness consistency in the generated audio levels. And we also make them mono because, our consistency autoencoder expects mono inputs. So as for the autoencoder, we use music to latent. It is a consistency-based model that works directly on monophonic complex spectrograms, treating the real and the imaginary components as separate channels. And unlike standard diffusion models, consistency models learn to produce the same output from any point along the probability flow ODE, meaning that this means that we can sample in one step by enforcing a so-called boundary condition, where each prediction, instead of predicting the clean target, each prediction must match the model's own output at adjacent noise levels. So you could see it as a way of you are distilling the model's knowledge of the next step to the previous one, right? And this coupled with a schedule on the step size. So at the beginning you only do one step, and you keep on, as you train, you keep on reducing this step until you cover all the denoising steps. So this training scheme allows the autoencoder to reconstruct audio in one single step, and this is without requiring any additional adversarial loss terms or whatsoever. So just one single loss, very elegant. So this in practice gives us fast and stable and high fidelity latent space, which is ideal for the downstream task under consideration. So the third block that I mentioned was CLAP, which stands for Constructive Language Audio Pre-Training, and is a joint text audio embedding model that lets Differif, as I said, understand both text and audio references. It has a text encoder and an audio encoder, and they are trained together so that matching audio and text pairs end up close to each other in the same embedding space. And this is done through the information noise contrastive estimation loss, which is basically pulled together positive pairs. So as I explained jazz with an example of a jazz player, and push away samples that are unrelated. So this shared space is what makes text prompts and references interchangeable, and we can use them as conditioning signals for generation, and frees us from needing text in our training data. So finally, the core of Differif, which is the actual generative model, is a standard convolutional unit, very similar to that described in DDPM++. We used 4 downsampling residual blocks, like the one shown here in the slide, with a self-attention layer in the bottleneck. We inject conditionings through side connections that go through these 2 dense layers, taking the CLAP embeddings and the diffusion time step, and feed them to every layer in the unit. For training, we also follow the elucidated diffusion model framework that uses a log-normal noise schedule, a variance-preserving style preconditioning for stable signal-to-noise ratio across the whole denoising schedule, and it predicts the clean signal, X sub 0, instead of the score or the noisy one. And it has also a time step aware loss function, so that all noise levels contribute equally to the gradient, and a deterministic ODE solver for sampling. This approach is a bit heavier than other methods, like new consistency models or flow matching, but it consistently gives some extra quality in inference, which is why we rely on this method. So we conducted some human evaluation, and we saw that Differif achieves audio quality on pair with real data, with no statistical significant differences between the answers that listeners gave to real and generated data. So we test the model in 2 settings. Of course, one generating stems, which is the default operation mode of the model, but we can also just feed back its output as context and create full songs in order to have a more fair comparison with other baselines like Stable Audio or Audio LDM2 or Music Gen, which were trained to generate full mixes and not individual stems. But even in those cases, we see that we significantly obtain better quality than previous state-of-the-art models. So let's watch a demo of Differif. So here we're going to give a context that this was pre-produced by my brother, who is a musician, and all the remaining elements will be added by Differif. So this is not working live, of course. This was pre-generated and created, so this is not a real-time model. right? So we did a follow-up of this work and trying to improve along some axes in terms of quality, diversity, and text control, which were still a bit not completely there for what we wanted. So in this follow-up work, we implement these key enhancements over the initial model. So first, we upgraded the original consistency autoencoder from music to latent that was working on monophonic audio to music to latent 2, which supports true stereo output with considerable improvements in fidelity as well, and also a double the compression rate. Second, we transition from the latent convolutional unit to a more sophisticated diffusion transformer architecture. And as we will see, these first two enhancements considerably boost the quality and diversity of the generations. And third, to refine the text-based control, we have trained an additional diffusion model that translates text to audio clap embeddings. So similar to this thing of the bridges. So we go from audio embeddings to text embeddings. So this approach attempts to bridge the infamous contrastive gap that exists in clap, by which text and audio embeddings lie on a disjoint manifold, so they are not completely overlapping, which produces a distribution shift at inference when you are using text conditionings. So yeah, the model doesn't know what to do with text really. So further, by using this probabilistic model, we can sample unlimited audio embeddings given a single text prompt, something that you cannot do with clap because it gives you a deterministic joint embedding space between text and audio pairs. So given a text, you cannot have many audios, and given an audio, you cannot have many texts. So in this case, by having this probabilistic bridge, we can do this operation, which we believe is an interesting control. So this we call clap beta, the bridge, and yeah, it gives you this auxiliary control that to sample many audios given a text prompt. So finally, by incorporating consistency training into the latent model, we can significantly reduce the number of denoising steps. So in the original work, we use EDM, as I mentioned, and we use 30 steps. And in this case, we can reduce down to 5, without a considerable loss in quality with respect to the original model. And yeah, we still obtain competitive metrics compared with the original differif. So we evaluated the proposed improvements against the original model through an ablation study using objective metrics. So of course, the well-known Frechet audio distance for audio quality, where lower values indicate better audio quality. For fidelity and diversity, we use density and coverage, which evaluate how well the generated audio represents the target distribution. And to evaluate how closely the generated music matches the input conditionings, we use the clap score for the text. And we also develop a new metric that we proposed in a paper submitted to ICAST last year, accompaniment prompt adherence, which assesses the alignment between context time series and target. So yeah, how well our generated stem fits to our context. In this case, higher values indicate better alignment. So let's now take a look at some of the results. So we can see that, all of these, in terms of FID, we see clear improvements. As I said, lower FID is better, except for the consistency. It's still, as I said, better than the original differif. But we speculate that by having what I was mentioning before in one of the questions I made, is that by having one-step generation or few-step generation, your input conditionings, the model doesn't have a lot of opportunity to inject the conditionings, right? So, and you cannot use guidance as much in a normal denoising schedule. So we think that this is in detriment of audio quality. I didn't put the results for diversity, but just for the sake of simplicity, but they are largely improved. And as you can see, in terms of adherence, we considerably improve the original baseline, except for text, this is something we didn't really get our head around, why the text embedding was worse for the new models, except for the club beta. Oh, I think I missed one value in this table. But yeah, except for club beta that we managed to keep it on pair. I think we are missing a one there. So yeah, finally, let me mention one of our most recent works that attempts to facilitate the introduction of new controls over differIF without having to retrain the model every time we want to add a new control. So for this, we add this appendix network to our model, which we call Lilac, and it's a lightweight version of ControlNet, if this rings the bell for you. And this simply attaches new controls to a frozen differIF. So we basically freeze the differIF. We don't need to update any of its weights, and we just add very simple blocks that take care of translating the new control into internal activations of the model. So this is done through, well, here in the slide we have in the left the original ControlNet that relies on having to duplicate entirely the backbone model. So basically no real gains. So you freeze the backbone model, you duplicate it, and you basically have a running replica of the same model that gets updated for the new condition. This is, of course, very expensive. So what we did is just remove this clone altogether, and what we do is to stitch sandwich layers to each of the layers of the backbone that are much more lightweight, very simple zero. Yeah, we just do some smart initialization of these layers with zeros or ones, so that at the beginning the model is just behaving as if there was no conditioning at all. And as it trains, these layers start to propagate errors, and they start to slowly move towards satisfying the input control. So let's listen to some examples from this new model. So here we have a context. So this is the input context. And this is our reference. So this is the model should be producing a violin to that piano. So here in the left we will listen again the context, and in the right we overlay the generated. Example. You already heard that, so now we use this as context and as reference the piano. So now we invert the roles, so now it should generate a piano. Oopala. Finally, I will play this one that is very cool. This is with texts, so this is the context. Voila, and we use electric guitar, distortion pedal, solo. And this is the generation. And finally, this one is some orchestral music. Oopa. Voila, violins, orchestral, ethereal. Voila. Some things to mention that I find very cool. So let me also mention that differIF also demonstrates a range of emergent de facto capabilities at inference time that include, for instance, what we call metaphorical synthesis. So basically, because it is trained on clap, it has this dark knowledge from all the data that clap was trained on, and it reinterprets, for instance, so clap was trained on sounds of whales, on sounds of storms, and the differif has learned to reinterpret these concepts in a musical way. So for instance, we can say things like, the rain is pouring on hi-hats, thunder is playing the kick drum, this drum kit sounds like a storm. So this is the prompt for this example. Voila. You can also do whales, and then the whales sound a little bit like a theremin and things like this. Like, it does really weird and cool shit. Other things that you can do is loop sampling. So yeah, you can, by playing with the structure of your noise input, you can impose structure on the generations. So you get repetitions. You can, of course, do also in painting. So here we have the input. We remove this. And we ask the model to in paint, to generate the missing fragment by, imagining it. These clicks that you hear, again, they are not from the generations. But many other, the ones I was mentioning before, textual interpolations, we can generate variations, and many other that we might even not have thought about. So going back to my initial slide about the prior works, we actually have made considerable improvements in all of the targeted areas. So in terms of sample rate, as I said, Diffusion operates on 48 kilohertz, also generates stereo music. Fidelity, according to naive listeners, at least, of course, if you professional music producers will detect problems, right? But at least broad audiences don't see any differences. Inference time is actually pretty fast. We almost achieve real-time factors on CPU. So basically, the problem is that it's not a causal model. So if you want to generate 60 seconds of audio, it takes around 63 on CPU. In GPU, it flies, like it generates 60 seconds in 4 seconds. The model size is tiny, 270 millions compared to, stable audio, which is 1 billion. Controllability, of course, there's always room for improvement. Modularity, we generate stems. And we generate, diversity is one single model generates all instruments, so except vocals, which we removed because they are very complicated, and we don't have, without lyric conditioning, it doesn't make any sense because you only have a babbling model, right? So what's next? I hope I'm not out of time. I think I'm fine. What's next? So of course, control affordances. Of course, controls are never enough. Well, it depends. Sometimes you want a little bit of surprise from the model. So I'm going to just say affordances in the way that if you want them, you have the possibility to follow that path. So at least to be able to let the user choose the degree of control. So we are working on many avenues in this regard, having MIDI conditioning, tags, voice control, maybe lyrics, of course, to have the vocal generation. We also have some projects in CSL involving dance to music. Of course, why not? Other modalities. Also inference time manipulations, tweaking the gradient fields that the model produces. I think this is very interesting. So like guidance, but without having to do additional passes through the denoising model. So in painting, feature transfer, guidance, blah, blah, blah. In terms of data, of course, we work on trying to find interesting augmentation strategies to cover as much as possible our target, the target distribution that we don't have. Working on source separation to increase our data, our STEM data, and of course without having the artifacts of the source separator leaking to the generative model. This is what we're working on. Also, evaluation is becoming more and more tricky because as our models are getting better, our metrics are not telling us the truth anymore. No, we might be measuring noise. We are in the end of on the region of these metrics that it is just we might be just measuring noise. So right now I'm not even sure how to interpret my FAD and KIT metrics, because sometimes I get models that this feels much better than this one, and my FAD is 0.1 lower, but this is the degrees of variability that I am getting at this point. That plus 0.1 or minus 0.1 in FAD, is it better, worse? We don't know. Also, the more we explore new conditionings, we need to derive metrics to assess whether the model is being responsive to these conditionings. And of course, quality and speed, it's always welcome. So we are exploring other diffusion algorithms like mean flows, shortcut models. I think somebody mentioned before, and difference transition matching, which gives more expressive modeling of the OD. So this is all from my side. I don't know if I have 5 minutes. Maybe
3 minutes.
3 minutes. Okay. So maybe you prefer to ask questions, or I don't know. Otherwise, I can show you Diffusion in action.
I think there's time for presenting.
All right. So here I already uploaded some music context. So right now I don't have any, I'm going to disable the reference. So right now it doesn't have any reference, so it's going to invent an instrument, and in this case it generated something here. Let's listen to it. All right, so like some weird shakers. If we don't like this, we can generate something else. So this is, running really on the fly. So what the fuck?
This is running in the computer or in the cloud?
In the cloud. It is running on a server. Voila. So this is generating. Okay, what else? Okay, let's add something weird. So let me try what I mentioned before. A whale singing like a theremin. Let's put text. Let's see if this works. Sometimes it's a bit capricious, let me stress that the model never saw a whale in the training data. It's just trained on music stems. So it's actually pretty amazing, this thing of the knowledge distillation from club. I don't know, a lion, roar, how do you say it? Roars a melody. Let's see. If you have a suggestion, please be my guest. So this is a failure mode of the model that sometimes when you give a very vague, in this case it's not, it's pretty vague, but when you give something that at the eyes of club falls into somewhere where everything falls, what it does is to replicate the context. So it generates something very close to whatever it was given at the context. We think this might be a result of that maybe we have on our STEM data either leakage from crosstalk from stems. So sometimes the context is informing a lot about the target. So an easy solution is just to copy it has learned to, when it doesn't know how to proceed, it just lets the context through. And it luckily it doesn't happen very often, but sometimes happen. I don't know. Do you have any? Yeah.
You try to just another failure mode, which is like a voice, just to see what it outputs.
Like choirs, it does it pretty good, but let me female rapper. Yeah. Let's try that. Let's remove the context to see if that helps, because it won't have anything to replicate. Oh, this is something, when in the unconditional setting, sometimes it generates a lot of silences. So this is a model that it has to be really densely conditioned, otherwise, of course, the task becomes extremely complicated. So unconditionally, it's a bit not very good. Pretty cool, but not a female voice. Let me maybe increase the guidance on the clap so that it has to do a female voice. Hopefully in my text, sometimes the ingredient of the text prompting doesn't get updated for some reason. So this is what I was mentioning before, that training on voice, if you don't have lyrics, it's a bit useless, because otherwise you will get these babbling voices that. Whenever we might be in the next iteration, we might have the model with lyric conditioning, and then we will do voice generation. All right, cool. If you have any questions, that was.
I have one. Have you tried using more steps? I know you have a consistency model, but you could generate a sample, then forward diffuse it, and then you could try to iteratively do this. I think they do this in the regional consistency model.
In this model, we don't use consistency. Consistency, we really tried it out, but it was actually yielding worse results than EVM. And the thing is that our inference bottleneck is really the decoder, that it's the heavy guy in all of these, of the autoencoder. So the latent model, 5 steps, 20 steps, 1 step, it doesn't really make a big difference. The bottleneck, it will still have to go through the decoder, which is non-causal, by the way, so we cannot really stream, not even stream. Okay. We did these kind of things. And this is what you're mentioning of generating noising, and we do this for the variation generation. So we generate something, we add a little bit of noise and denoise from a partial point in the denoising schedule to generate a slight variation. And you have some variation strength. The more strength you want for your variation, the further away, the more noise you add, and further into the denoising process you go.
Okay.
And
And I have another question. Do you know if just with the text prompt you could get musical information? For example, if you ask piano without the context, if you ask for a piano melody in C major, something like this, do you know if it will be in C major, or do you actually need the conditioners from Lilac?
This doesn't have Lilac in this one. I'm not using Lilac. But let's try. Sometimes it has done these things. Maybe C major, it picks it up. I don't know exactly the it C major?
Sounds major effect on.
It is major, I think it's.
That's the thing. The mode it picks it up more or less. I'm not sure about the exact scale, but it depends all in the training data. I don't know what's the internal representation of club. So this is another thing we are doing now, updating a little bit also club. We don't know what training data was used about the legality, so we are trying to build our own text embedding representation space. Also using more modern techniques like SLAP or these Siamese networks. And yeah, like we will also make sure that it has more musical language in the training data, because as far I don't know about the in and outs of the data of club. So yeah.
Just a question. So here you generate the accompaniment to the context. Can you do can you change the context with the text prompt and then use
No.
it later to generate?
Like the context doesn't have any effect on there is no generative or controllability over the contexts. Because this cannot generate more than one instrument at once. You can put the context as a reference, but again, it's probably going to just because this is taking you into a unseen position of club, so it's not going to understanding. So who knows how it's going to react? But yeah, no, you cannot have any effect. What you can do is with text. You can, for instance, put a guitar as a reference, and this guitar might not have pedal distortion. And in the text prompt, you say a guitar with pedal distortion. And then you will get as the output a guitar that looks like your audio reference one, but with distortion. So you can have this one-shot style transfer and kind of universal control. A guitar with reverb. You put reverb on the prompt, you put whatever guitar you want to add reverb to, and it will generate something like that guitar with reverb. So it has these one-shot capabilities as well that are pretty interesting.
Is it possible to mirror the original signal on purpose? Like I want this guitar and...
You can do that with by doing what he was saying. You can add a little bit of noise to that guitar and then denoise with whatever text prompt and create variations with that text prompt conditioning. So,
in which domain are you adding noise?
sorry?
In which domain are you adding noise?
In the latent domain, so
Okay.
we are using the music to latent space, so it would be on the latent space of the model.
Nice. So, any questions? More questions? No? Well, thank you.
Thank you.